Okay, everybody, welcome back. This is day number 2 of the first weekend session of the Unix operating system course. And this morning is about the kernel, and then this afternoon will be about kernel services and more Unix related topics. But to kind of give you a full background on the kernel concept, this is lecture number 2A, and there's a 2B as well. So we'll cover Unix first in terms of the kernel, talk about kernel mode, user mode, and then switch into some other topics, because this is really the core of Unix in terms of the operating system. Actually, when you think about Unix in general, most people think about the kernel, and they don't necessarily even consider anything else as part of the operating system. I mean, like, the kernel is the brains of the operations. In the DOS world, it would be like the command.com or something. I mean, it's the interpreter / brain. And then, I don't know, they call it kernel because it's like in the center of the apple or center of the fruit or center of the operating system in terms of the information. So there's been a lot of motivations throughout Unix development throughout the last, through time since the beginning. The knowledge of the Unix internals can help you understand the different breeds of Linux and Unix, and design for performance for different types of applications. Why some Unix variations actually work better than others and stuff like that for different purposes. So what is the kernel? Well, it's part of the operating system that contains the code for, and that's the interesting thing, it's code. It's a software program. So it's usually compiled in C, and it's done because, going back what I said yesterday about the C language and the relationship with that in Unix and Linux. We have a kernel in a Unix mode. Unix box. We have a kernel in a Linux box. We have a kernel on a Windows machine, believe it or not. We have a kernel on a MacBook. The kernel as a concept is controlling everything. It's controlling the execution of processes from the creation, termination, suspension, communication, anything associated with running programs on the computer. It's also in charge of scheduling processes, keeping fairness between the use of the processes and the CPU. Because basically the job of the operating system as a core is to provide the interface between the hardware and the user applications. So the kernel, is generally the definition of what the services are that are going to be provided from an operating system perspective. And still in the modern day computer, even on Unix is a little bit different, but in modern day computer we still have singles, doubles, triple CPUs. Most of the jobs that are running through the operating system are scheduled together. So we have different job levels, different process levels in terms of execution of programs, different priorities, as we talked about yesterday, different functionality. And usually at one moment of time, one CPU is only providing instructions for one process. So unless you have multiple CPUs, you don't really have that much CPU multi-processing going on. So we also think about the thread abstraction as well, and kernel level threads, which are nothing more than processes of execution to be scheduled. So the kernel is the brains, going back to that comment, which means it's responsible for all of the data that's being held. So it has data structures, as an example, a PCB, process control block. It would hold that in memory, kernel level memory, to keep track of running processes, CPU scheduling, file management, file I/O. I drew a little picture before the class started. Let's see if I can find the picture, actually. Let me put the picture up. Here's my lovely picture, a drawing for today. If I had a blackboard, I'd put this on the blackboard, or a whiteboard, or a chalkboard. But if I put it on this board, you can't see it, because a slide would go over it. But normally people usually draw a box, and they put a user mode on the top, kernel mode on the bottom. They draw this distinct line between the two of them. And the line actually signifies the separation in terms of what's referred to as modes. And there's a switching that goes on between kernel mode and user mode. Oops, I misspelled kernel. That happens throughout the course of the execution of the operating system in terms of the functionality. And what's going on is we have certain jobs, certain functionality that is only performed by the kernel, and then certain functionality that is made for users. What do users do? Users run programs. So what does the kernel do? The kernel provides that interface to the hardware. And so they're capturing and storing and keeping track of interrupts that are occurring. The kernel is keeping track of the memory usage on the computer in terms of the hardware. This stands for PCB's process control block, disk managers for hard drives and CD-ROM drives and stuff like that. Kernel loads on the support for the operating system's file system. So you can get like Win32 or FAT32 or all the different types of file system support to support the information that's being read from the hard drive. Miscellaneous services to the user. So if I had a drawing tool, I draw an arrow and point it going upward. And then on the user mode, I draw an arrow and have it pointing downward, meaning that we have a two-line communication, which is why they usually refer to this as a dual mode configuration. And dual mode because we have two modes that are running simultaneously. We have that kernel mode and the user mode. And what controls the interface between those two modes is referred to as the system call interface. So when you took, as an undergraduate student, when you took your first programming course, they taught you about APIs. What's an API? Application Programming Interface. And they said, well, everything out here is application. Everything in the user mode is an application level. And everything in the kernel mode is a system. Or could be referred to as a system level program. And the APIs are a wrapper. They're an interface on the system call interface. And the system call interface are the low-level fork, write, read. They're not too fancy, but they're the commands that the user would send from an application program to the kernel to have the kernel do something. And so the user mode communicates with the kernel mode through the system call interface, which provides the communication channel, essentially, to get through this firewall here, this line that's drawn between the two modes. And then from the kernel mode to come back up to the user mode, well, the kernel mode is going to send an interrupt up, or it's going to send a signal to say, hey, you know what, the CD-ROM drive door is stuck, it's not open. You're trying to read something, but there's no disk in the drive or something like that. And so kernel does communicate with the user, and it's usually through sending information that can be caught. So we have different types of interrupts that occur on a Unix system, and it's very similar to actually the Windows system as well. From a hardware perspective, a hardware can send a hardware interrupt up to the kernel, and the kernel, in fact, I'll put here interrupt tables, interrupt vectors. Interrupt tables. The kernel keeps track of all of these things because interrupts are kind of interesting. They're like signals, usually from a hardware perspective, coming up, and the kernel has to catch them and store them because it might receive more than one, and it might receive simultaneous information. And then as the information is gathered, it's usually put into an interrupt table, and then there's a code associated with each one, which tells the kernel what it's supposed to do. So the kernel at one moment in time might be having to close a door, open a door on a CD-ROM drive, open a file, open a hard drive, mount a hard drive. All these sort of different commands that the user actually, all this work the kernel has to do. And the user doesn't normally receive them, but the user can actually generate its own kind of interrupt by using, basically a software level interrupt to signal to the kernel to say, hey, stop that program from running, take that out of memory, clean this up, things of that nature. So there's a lot of communication that goes on between the two modes, and the form of the communication is really what's describing the operating system and what's going on in terms of the abstraction. So without the kernel, the user mode would have to deal directly with the hardware, which would be kind of tedious. Every time you wanted to write a program to do something, you'd have to actually start from scratch and figure out, how to, basically work with the hardware and how to write that, how to write the interface. So the kernel, by having this concept, can load up at one time at the beginning when the computer turns on, and it can load I talked yesterday a little bit about kernel loadable modules and things of that nature. It can load modules, and the modules will have driver support for hardware, recognize the devices on the computer, and basically provide that service of the interface. And once the service is there, it's consistent. So all programs can use the same application programming interface to work with this as well. So, and from a C perspective, because Unix is a C-based program, the IOstream.h, the stdio.h works directly with, and we talked about this yesterday, the three IOs, the standard input, standard output, and standard error. And it works directly on top of that. And so the open close is actually more of a system call the low-level calls and the usage of the standard I/O. The wrapper is the stdio.h, which would be the C header file that gives you the printf, scanf, and those are API calls that call underlying system calls. So we have think of it more like a layered abstraction, and the higher up you go in the layers, the easier it gets, and the lower you go down in the layers, the more tedious the programming effort is, and the harder it is to actually write and use programs at that level. So people like to work at a high level. They like to go up to the highest API level to write because it's easier. I mean, we have buffering and we have all sorts of different utilities that are mixed in with that. So let's go back to what the kernel is responsible for. Allocating memory for the execution of processes, allocating secondary memory, handling peripherals such as terminals, tape drives, disk drives, network drives, all sorts of different hardware pieces of that nature. So some kernel characteristics in terms of, it's a program. It's a running program, mostly written in C and some assembly language. It's written in assembly language for driver interface, for efficiency, and plus you can't get too high level down there. If you think about the generations of programming languages, to write a kernel, you can't do that in like Visual Basic or something because there's no support for underlying .NET. There's no support for Java. So you're going to pick a language that's pretty hardcore in terms of basic low-level implementation. The kernel, it gets loaded into memory and runs until the system is turned off or it crashes. So when you turn the system on, in terms of the boot up process, the kernel is the first thing that gets loaded, and then the kernel loads everything else on top of that. So it's kind of, without a kernel, you have no operating system, essentially. And it's kind of funny because kernel is just a file. It's an image file. And it extracts out, opens up, loads stuff into memory. And all of this is nothing more than a memory abstraction, if you think about it. You're loading a program into memory that's acting like a kernel, and that memory is a program, and that program is keeping track of the services, providing you that kernel interface. So user programs make use of the kernel services via the system call interface, as I mentioned, provides services transparently to the rest of the system. And transparently is kind of interesting. I don't know if it really, if you think about it as being transparent, when you make a system call, you're pretty much like, obvious, you're talking to the kernel. So in terms of subsystems, this is kind of this is not a complete list, by the way. This is just a summary of some of the subsystems that are associated with kernels. The file system is a big one. Directory, hierarchy, regular files, peripherals, multiple file systems that might actually be supported. Because if you think of the concept, what do users do on their computers? They open and close files, and they manipulate files, and stuff like that. So in terms of features, it's nice to have a kernel that can work with a file system. Process management as well. So that would be how processes are sharing the CPU, the memory, signals. So, and going back to what I was saying about interrupts, and we would call that software level interrupt a trap, and we would call most of the signal behavior as sort of /interrupt/ trap kind of calls, because some of the signals, are software generated. Some of them come from events that occur in which an interrupt may have been captured or something happened. So signals are kind of an interesting interface. We also have I/O support on the operating system for processing, accessing terminal I/O. Terminal meaning the shell environment, reading and writing to that, as well as GUI and stuff like that. Memory management, System V and BSD have different implementations of different types of subsystems as well, which is kind of the interesting thing about Linux systems. So in a Unix operating system, we don't think of the file system as part of Unix. We have I was going to call them third party, but they're external usually in concept. As an example, if you're running with a Windows box, you're usually looking at, from traditionally a FAT32 or FAT12 or FAT16, which is FAT standing for File Allocation Table, which is nothing more than the organization or the structure of the files that are stored on the disk. And if, for example, you were running you had a Unix box or Linux box and you wanted to load on that FAT formatted disk, then you would load on a file system support for FAT. And if you wanted to run extended 32 or extended 12, extended 2, you could load on file system support for that, or for journaling for the OS X or something of that nature. So it's really kind of an external concept. Not really, I mean, the kernel doesn't have like hard set file management in terms of this is the way you have to store kernel supported files or Unix files. There's not really no such thing as a Unix file. It's file systems. So, and more operating systems are actually becoming more generic. Like you can load Windows files, on a MacBook. And software vendors, such as Microsoft, are making generic files now. A .doc, a .ppt, an Excel file now works the same regardless of the file system. So we're getting a lot more compatibility across different types of file systems and features. In the old days, if you had created a file on a Mac and it was a doc file, a Microsoft file, actually Microsoft wasn't supported on the Mac for a very long time. And then when it finally was supported, that doc file didn't run the same. You had to convert it to go to a Windows machine. So that was one of the best things that happened when the MacBook actually switched over to a kernel and switched over to a Unix, because in the past it actually wasn't a Unix-based operating system. I mean, it wasn't. It was similar, but it wasn't a true, Unix support, extendable, expandable kind of system. Instead, it was like, it was Apple. It was like Windows. It's just proprietary. So now that it's opened up a little bit, you can load open source. You can download Linux and Unix utilities and tools for a MacBook, and it's just like a regular old Linux box, which makes it flexible and makes it more compatible with others. So talking to the kernel, as I mentioned before, we're processing kernel facilities through system calls, as they're called, system calls. And the privileges communicate through what's called hardware interrupts. And this execution in user mode and kernel mode contains several different data structures, and they're needed to implement the kernel services. So this is not a complete list as well, but this is just an example. For example, the process table, which contains entries for every one of the processes in the system. We have the open file table, which keeps track of all of the open files that are in the system. You might be wondering, well, why do we need to keep track of all that stuff? Well, it's really important if you want to multitask. So if you have multiple processes running, you want to keep track of them, and you want to make sure you can schedule them fairly. And same thing with files. And then files opened by user as well. It's kind of important. So in terms of the execution of the user mode and the kernel mode, so when a process executes a system call, the execution mode of the process changes from the user mode to the kernel mode. So we actually, the user never actually enters kernel mode. The user is always in user mode. But the thread of execution changes. So instead of you running something yourself up there in user mode, the kernel actually runs something. And it's a call from an instruction that it was given to open a CD-ROM drive, or get a file from the hard drive, or provide some service, some interface to the hardware. So processes in user mode can access their own instructions and data, but not the kernel instructions and not the kernel data. You could never get what interrupts are in the process table, or excuse me, in the interrupt table, or which processes are in the process control block. You're never going to get that information. So it's protective. So one of the reasons why the Linux kind of environment is so nice is because you can create a pretty stable operating system that can't be hurt by the user mode, and yet you could still open the whole entire system up for user activity. As long as you block the kernel so that the user could never go down and touch any of the kernel data structures, can't access the memory, can't do anything with it, then it's protective. So, I mean, we want a computer that's going to run. We want a system that's stable. So one of the things is, usually they call it protected mode or something like that, because what they're referring to is that level of protection you have by blocking everything so that the user can't go into kernel mode. So the kernel mode itself, the process can access data structures such as process table and everything else, but it's the process that's accessing it and not the user. So here's an example flow of control during a system call. What happens when a system call occurs? And to refresh your memory, a system call is when the user asks the kernel to do something for itself. And one of the common system calls is open. Open, read, write, close. Those would be considered system calls. So the user processes or invokes a system call, for example, open. And then every system call is allocated code number. So open is human readable. So you gotta put that into like a number, hexadecimal number. So 15272. I don't know, some number that the kernel is gonna keep track of. And each system call has its own number system. So the kernel would look up and say, well, what number is this? It's this number. Oh, goes with this device, and this is the instruction I'm supposed to do, and here's the program I'm supposed to run when I receive this. It's kind of like, when you have an assistant and you say, here's a stack of papers, go make photocopies. And then so she knows how to make photocopies. So she takes the stack of papers and finds the copy room and does everything automated for the person who has requested the copies. So we have a C routine library version of a system call places system call interface, and the version places the system call parameter and the system call code number into a machine registry, and then it executes what's called a trap, and a trap is a software level interrupt, and a trap is a machine instruction switching from user mode to kernel mode, kernel code to kernel mode, essentially. So it's telling the kernel to go do something, which is the form of communication from the user mode to the kernel level. And then from kernel code to kernel mode, the kernel code itself initiates the trap, and it switches the execution to the kernel mode. And most people go, well, what do you mean by kernel mode and kernel code? And, well, the kernel has instructions, and it's a program that's running. Just think of it that way. But is it really running? Well, it's paused until it receives an instruction. So when it receives the instruction via the via the system call interface, it generates a trap to tell itself, okay, start running, wake up. So it's kind of like thread processing. You can sleep, wait, all the different states that the active thread can go through throughout the life. Well, the kernel's switching states too. And they say it's in kernel mode when the kernel's running. It's not paused anymore, it's actually performing something. And we know this all the time. Actually, how many times have you looked down at your computer and seen the lights on, and it looks like something's going on, but you're not doing anything. You're just watching TV, and the computer was sitting next to you and it was turned on or something. But it's doing a bunch of stuff. Well, that would be kernel mode activity, actually. Or background processes in the user mode that are updating your system or doing something like that. So the flow of control of the system call, the trap instruction uses the system call numbers as an index into what's called the system call vector table, which is located in the kernel memory. So the kernel memory, that's an interesting concept. When the kernel boots up, which is the operating system starts essentially, generally takes the lowest end of the memory and loads itself up to a certain point, and then user mode starts at a certain level in that memory. So we have pretty much sequential contiguous memory allocation at the lower banks, which makes it faster to access. Because if you think of the concept, do you want to make the memory fair for everybody, for user mode and kernel mode? Probably not. If you give the kernel the best memory locations, well, anything closest to the CPU is the best memory location. So we have different types of memory. If you take a computer architecture course, you learn about that. Or a general operating systems course would give you that background. But just to give you sort of a summary of the big picture, memory, the closer you are to the CPU in terms of the architecture, the smaller the memory and the more expensive it is, and the faster it is. So registers, as an example, are used by the CPU directly to hold data, and it's a different form of memory. Cache memory, which is a little bit further away, and then we have the DRAMs, and then we have the hard drive. Hard drives are cheap compared to registers or to caches. So bigger hard drive, smaller caches. So smaller register space, more expensive, slower. So you wouldn't want to run, which is why it's nice to be able to. And yesterday I showed you where to go for Ubuntu, and I said, well, you load it and run it from a USB drive if you want to, and just plug the boot to the USB drive. That's going to run pretty slowly, because you're running an operating system from the worst memory possible. It's being loaded in a USB drive. Not to say that that's the worst memory possible. It's not bad memory. In fact, it's expensive memory in terms of the concept, but it's very far away from the CPU. So everything that gets processed from that USB drive has got to go not only through the USB channel, the I/O port itself, but it's got a long ways to go before it can get CPU action. So that's why hard drives are normally mounted closer. They're on board, or they're, the IDE interface or the SCSI interface is directly connected into the I/O, and there's a stronger, faster channel. Not only that, and then nothing runs from the hard drive. Instead, the kernel gets found on the hard drive, and then it gets loaded up into memory, and then everything runs from memory. So memory is kind of an interesting concept. It's like your entire computer is just memory. So I mean, you're not really doing anything. It's just memory that's working. So it's important to have fast memory. So you want a fast computer, get fast memory. That's essentially how your computer's going to run. So okay, so going back to the slide, the system called vector table is located in the kernel memory, which is an array of pointers. Pointers to kernel code for each one of the system calls. Pointers. And nobody likes pointers, but pointers are kind of fun because why actually load everything? Instead, you can create pointers, and then the pointers can load it when it's needed. So in a lot of ways, we have just-in-time kind of code loading. And we have small kernels. And the concept of that monolithic, and I'm going to go through that in a few minutes, but do we put everything all in one and we just have one kernel? Or do we separate everything out into multiple level of support, multiple drivers, multiple everything else? It depends on flexibility. It also depends on how fast you want it to run. If you put everything in one and you load it all at the beginning and when you turn on the computer, everything's loaded into memory. You've got a single kernel kind of brains of the operation. You're going to get a fast system. You're going to get a fast system that doesn't take up too much memory. That's going to load pointers for other code, and those pointers are going to be executing kernel instructions quite quickly. However, you add a new piece of hardware on your computer. Kernel don't know about that. Yeah, rebuild the kernel. So because it contains only the drivers that it's aware of, it's pretty small. And actually, size is interesting. People think, well, if you've looked at and have ever tried to build a Linux kernel, it's actually kind of easy. You download the source code for it. You run through a kernel configuration program. It's GUI these days. You type a couple of commands in there, and voila, you got a kernel image. And then you tell Grub to boot this kernel instead of that one, and now you have a brand new operating system, right? But when you ran through that configuration and you decided what modules am I going to load, what you're doing is really picking out what hardware do you have on your computer. Do you have a CD-ROM drive? What kind of memory do you have? How much memory do you have? What kind of management do you want? Do you want to run from a swap drive and stuff like that? And the concept being, you're only loading into the kernel what's needed. So Microsoft is sort of the exact opposite of that. If you installed Microsoft and you have the system, you have support for everything. You have drivers for hardware you'll never own. You have any possible configuration on that hardware is going to be supported. So Linux is the opposite. When you build that kernel, if you're building your own kernel, it's customized. It's only the hardware that's on your computer. So when your hardware changes, So Linux people, Unix people are always looking for drivers, writing drivers, downloading drivers, installing drivers, rebuilding kernels, upgrading things. Because they're trying to go for efficiency. They don't want to include everything but the kitchen sink in there. But at the same time, they want to include the things they need, and stuff changes. So, and then also, think of the concept, brand new hardware. We've got a driver for it, So it's kind of hard to find open source support and drivers for hardware that's brand new. In fact, now I'm happy to say the USB support's pretty good. But in the beginning, when USB was really becoming popular, nobody had any drivers for that. So I mean, this is like a while ago, but now we got USB 2.0 support. We got everything. So when you download Ubuntu, if you use that option and you install it, you're getting sort of a Windows Linux kind of concept, because Ubuntu is going to have one kernel, but it's going to have everything loaded in there. So it's going to be a big kernel. And the advantages you have of building your own kernel is you can make it smaller. Well, why do you want to make it smaller? Well, you're loading less stuff in memory. The less room the kernel takes up, the more room the user can use. So you have less swapping going on. And it just runs faster. So you don't want to load everything in memory. So you build your own kernel, so you have a small memory footprint. And also, the kernels, it's kind of an interesting concept. It's used a lot for embedded devices too. So let's say you built this nice little product. You know, you went out and you had a company build a board for you, and the board is like, you know, single mode, single computer board, no interface or anything, just an LCD and a touch membrane pad or something like that on there. Well, you build your own kernel that only has the touch membrane pad and the LCD interface, you know, the drivers to control that, and then you write little programs. You know, when you press this, turn the heater on. When you press that, turn the air conditioning on. And then you have, well, you know, a temperature controller, or you have a microwave controller, or a, you know, dishwasher controller. And it can be written in kernel. It can be written in a kernel, and you have one kernel you load on, and it's really just one program. So you want to make an update to your temperature controller. Hey, you just swap it, build another kernel on another system, and then swap it. Download it to the hardware on the device, and voila, you have created a new operating system and a new functionality. So the code corresponds to a system call, executes the kernel mode, modifies kernel data structure if necessary, performs what's called a return instruction that flips the machine back into user mode and returns the process's code, returns to the user process's code. That's just the same as a return in C. So when you learn C, which is actually not a bad language to learn if you're a computer science person, because it's Unix. It's basically telling you a lot of the underlying system implementation details that call, return, parameters, codes, vectors, all that stuff is part of programming. So in Unix we have a function call, and the function call has a return, which is the same as C. So that return is going to come back up, but in an operating system perspective, from a kernel mode, it's going back to the user mode. So that return comes up. So, in terms of synchronous versus asynchronous processing, which is kind of an interesting concept, do we really have synchronous processing on a computer? That's a very philosophical question for a Sunday. No, we don't. We have asynchronous. We don't have well, we're synchronized, but we're asynchronous. Nothing's happening, and nothing's really happening in real time. It's all scheduled, and only one process at a time is running at any one moment per CPU. So now with the advent, you know, the invention of the multiple CPU system, fantastic, because we could really, truly double the speed of the computer if we wanted to. If we're keeping those CPUs separate. If the CPUs are bound together and they're running together as a unit, we only have one CPU. Which is kind of interesting, you know, you see dual CPU system, dual. Okay, so if you have a 8, let's just use numbers here. If you have the number 8 and you divide it out 4 and 4, do you have anything more? 4 plus 4 is 8, and you have 8. So if you have a dual processor that runs, you know, divide the processor speed in half and stick it into 2 separate processors and then put them together. It's the same. But if you have 2 really fast processors, then it's like you have 2 8s. Well, that's 16. You've just doubled what you have. So there's a lot of games in the entire, you know, computer industry. Oh yeah, you can have a quad processor. I could have, you know, I could take that 8 and divide it out into 2s and have 4 of them. Now I got quad power, right? Yeah, it's the same. They're just itsy-bitsy little processors that are all acting together. Well, why don't you just make it single processors and put 8 of them on there, all working at the speed of 1. You know, so then I got 8 total. I still got, at the end of the day, you still got the same processing power. Long story short. So the trick is to get a system that has, you know, if it's going to be a dual processor, you know, don't have 2 itsy-bitsy little ones working together. Have, you know, power. Have really good ones working, and then have it separated out, and then have operating system support for it. So loading like Windows Vista, or loading like, you know, Microsoft, even XP doesn't really support dual mode processors. 7 does. 7 will run faster. It takes more advantage of the CPU processing power of the modern day computer. But if you load an old operating system, let's say on a brand new hardware device, you're not using the hardware, which is kind of interesting. So then, you know, through time, there's always that thing about vendors, you know, software vendors and hardware vendors, which is kind of interesting. You know, there's a split. Software people don't make hardware. Hardware people don't make software. But they're both working together. So if you've got a computer that supports something it'd be nice to have an operating system that supported it too. So that's why a lot of people go the Unix route, because, well, then you can make it support it. You can write your own program. Let's say, for example, you actually have a dual processor. You have two processors, and they're not running together. They're separated out. And you're running an application that wants to do some encoding. Then you create a synchronized system where both processors are running simultaneous. And one of them is doing translation of something, and then the other one is processing video or something, which is what we get now with the GPUs. So if you install a graphic processing unit, you have a graphic card that has a CPU on it, they call it a GPU, you have two processors. You have a separate processor on there. You're running in synchronous mode. Everything's running together in real time, and your graphics are coming out beautifully because it's not eating up your CPU power. Your CPU power is doing number crunching and working on some other process. And if you split the work off like that, then you have a true synchronized kind of processing environment. And if you can do that with the kernel in the user mode, then you have true harmony on the operating system. So usually processes performing system calls can't be preempted. They run and then they're stopped. Do you really want to tell the operating? It's almost like building a house and removing the foundation. Do you really want to burn the foundation? No, the house is going to fall down. So concept is you have to let the kernel run. You have to let the kernel do what it's supposed to do, and the user can't preempt that. So preempting means stopping something before it's finished. We never preempt anything from a kernel mode, which is, we'll let the user wait. But we can always preempt, excuse me, I meant kernel mode. We can always preempt the user mode. There's no problem with that. The user can just start the program again if they want, or they can do something else. But so we have a priority that's set. So a process must relinquish also the voluntarily the CPU, for example, while waiting for an I/O to complete. So that the kernel basically is in charge, and it has to voluntarily use the CPU, not use the CPU, run until it's finished, and not be interrupted, which causes, do we have synchronization? No, because the user's not doing anything while the kernel's running, and the kernel's not going to be preempted for the user. So we take that multiprocessing away momentarily while the kernel is performing an instruction, and we're really running in an asynchronous instead of a synchronous kind of fashion. You can always think of asynchronous as email and synchronous as chat. Chat sessions are happening in real time, everybody's talking to each other. But it really isn't, you can't actually talk together. It's two-way, you're reading and then you're writing, you're reading and you're writing. But if you were yelling at each other on a telephone, that would be synchronous. And the kernel doesn't yell, so it's not going to work in a synchronous fashion. Instead, it's going to work asynchronously. So the kernel is going to send a process to sleep, and we'll wake it up when the I/O is completed. So it's constantly juggling work and going to sleep and waiting and waking back up. So the scheduler does not allocate sleeping processes any CPU time. So they're not really hurting anything in the system. They're not eating up resources. But it can allocate a CPU to another process while the hardware device is servicing an I/O call. So we do have kind of a synchronization. It's kind of like a circus going on in the computer. So. Interrupts and exceptions. So Unix allows the device, such as an I/O peripheral or a clock, to interrupt the CPU asynchronously. So it can send a flare-up signal and say, hey, you can't read from me because I have a bad cluster. And then the kernel can say, oh, you have a bad cluster. Let's go tell the user. Bad cluster, bad disk, scratched disk or something. Problem. And it's really not that informative. Instead, you have these weird messages that come up. And if from a user mode, you can do exception handling. Say, well, if we have a bad disk, and we have a problem reading or writing the file, then tell the user this so that the user can close the program, or try another file, or try another disk. So in receipt of an interrupt, the kernel saves its state itself, so it's context, so it's frozen. So we have a frozen image of what the process was doing, determines the cause of the interrupt and the services of the interrupt, and performs the associated activity. Because if you think of the concept, even if someone's throwing flares up Are you going to see all the flares, at the same time? No, you're going to miss a couple of them. So everything is essentially queued, and the state of the process is frozen so that the kernel can actually deal with the information. So devices are allocated, and the interrupt priority base is based on its relative importance. In most systems, the kernel has everything is higher priority than the user mode. So all of the processes are definitely running more often, and they're getting more CPU time. So when the kernel services are services an interrupt, and here we have it's kind of bolded word blocks, because it does block. It blocks out lower level interrupts so that the higher level interrupts can work. It's kind of like when you problem solve and you say, well, I don't have enough money to pay my rent, so I'm going to spend all of the money, I'm going to pay the rent with it. But in the meantime, I have no gas in my car. So what am I going to do? Well, all right, you're going to block paying the rent for a while until you put gas in your car. And then you're going to wait a little bit because you have a paycheck coming in. So, which is how people juggle their finances. Some people, who juggle their finances. Unless you happen to be independently wealthy, you are basically putting priorities on your spending, and you have a budget. To talk about next door's finance class. The budget is what the kernel is doing to budget its time and money and resources to make sure that all of those interrupts and things are being processed correctly. It certainly isn't going to spend all of its money on a trip to Las Vegas or something, or it's because, it knows it has to pay rent at the end of the month or something. So it's definitely going to allocate in terms of its priorities. So processor execution levels. We have the kernel that must sometimes prevent the occurrence of interrupts during critical activities to avoid the corruption of data. As an example, the kernel is writing a file to the hard drive, and interrupts are happening because the CD-ROM drive is complaining about something. You're certainly not going to pay that CD-ROM drive any attention. You're going to wait, because the activity that you're doing is going to be a little bit more critical, and you're going to have some corrupted data if you stop writing that file and go deal with the interrupt. So I always say it's kind of like parents driving kids in a car, and the kids are in the back screaming. Are you really going to take your eyes off the road and turn around and go deal with the kid? No. You're going to we're going to wait a few minutes, pull over to the side of the road, then go have them shut up. So it's kind of like what the kernel does. It's going to wait. It's going to pull over to the side of the road, and then, after it's done, when it's safe, it's going to go ahead and process everything. Everybody else is yelling at them to go do something, We're not happy. Okay, well, so, process something, go do something else. So there's some typical interrupt levels. Machine errors, clocks, high priority disks, networking devices, terminals. So this is really the high level, and this is the low priority. Software interrupts, this is everything the user does is very low priority for the kernel, which is kind of sad, because the kernel's there working for us, but everything we do and everything we ask it to do is last on its list of processing. But as an example, if we have a hardware error in a machine level, the computer's not going to run, so we must deal with that first. So we're going to need to process that machine error and figure out, well, what's going on? Oh, the CPU is overheating. You have to excuse me, my voice is now starting to crack. So the CPU is overheating. So we have to deal with that first. Or we have a clocking issue, or we have the disk isn't spinning correctly or something. So depending upon the priority, it's going to get attention, and it's going to be dealt with. So, and it's terrible. User mode's on the bottom, and software interrupts are on the bottom, but that's kind of like how the system has to work in order to keep it stable. So in terms of the interrupt, they're serviced by the kernel, and we have what's called interrupt handlers that must be fast to avoid losing any of the interrupts. If an interrupt of a higher priority occurs while a lower interrupt is servicing, nesting will occur, and the higher interrupt is serviced first. So just because the lower stuff has got a chance to run, it may not necessarily run if something higher comes in. So it's really a queuing system, and then there's a check on the queue to see, is there an interrupt in there that should be running right now? If not, just continue processing what you're doing. So the disk architecture is used and is recognized by the kernel itself. The disk itself is split out two ways. We have kind of like a slice of pizza. So the sliced like a pizza called a sector. So if we divide everything out into sectors, and then we can subdivide out the concentric rings, and we call them tracks. So we have tracks and sectors. And this is really old technology. I shouldn't say that. Your disks, actually not mine, not yours. We all have solid-state drives now on the Macs, but the Windows people, they're still using those. Well, no, there's solid-state drives on the Windows systems too. But the basic future of disk architecture is no moving parts, and make it all solid-state. Make it all, it's still going to be magnetic-oriented, but or maybe not. Who knows? Nanotechnology in the future, but. Long story short, the more moving parts you have, the more that's going to break. And so old disk architectures had moving arms, and you had to go out and find information on that disk because it wasn't stored contiguously, and you had to put the pieces together, and so the kernel can wear out a hard drive, long story short, by having a really bad disk manager, a really bad algorithm that goes out and finds stuff and just exhausts the ARM completely. And so older systems actually did that. So you can actually optimize the way that the kernel works with the hardware, which is why this slide, this whole concept of disk architecture is mentioned in a kernel lecture. We're talking about kernels. Yeah, the kernel can actually wear out your hardware. It's kind of like your temperature controller can wear out your heater system. If it was turning the heat on and off every 5 minutes because it was 1 degree off, then it's going to prematurely wear out the hardware. So one of the jobs that the kernel must do is don't wear out the hardware. Make the hardware last longer. You do that by coming up with, utilizing the disk architecture and the functionality of how things are stored and optimizing it for retrieval and for writing, for getting to and reading from these hardware devices. So I'm not going to go through the architecture of a disk. It's really not. It's above and beyond the concept of this lecture. But we do have, typical blocks that are holding 4K bytes, and we have several different variations of the hardware. One of the biggest issues is that sequential reads that are much faster than random ones. And if we're not going to store things sequentially, how are we going to get the kernel to read those blocks in an efficient manner? So we want to conserve data, we want to make sure it's all on the same track. So a lot of operating systems and kernel operations do things like defragging the disk to get rid of holes in between, empty spaces between filled blocks and stuff. A little bit of memory management, garbage collection goes out into memory and says, hey, is this program being used anymore? No, clean it up. So the kernel is responsible for this type of activity, for maintenance essentially, and for I/O actually as well. And speaking of I/O, the file subsystem. So what is really I/O giving us is support for regular files, directories, special files, corresponding to peripherals and tapes. Everything in a Unix or a Linux system is a file. So Windows people are trained that a file stores data. A file is a file. It's on your hard drive or your USB drive. In a Linux environment, a Unix environment, your devices are files. So your directories are files. Everything is a file. So it kind of like flattens out all those other concepts in terms of the hierarchy of different items and puts it all into a generic file in terms of its concept. So we have file numbers and file descriptors. And the file descriptor is the pointer, because as I mentioned earlier, the kernel loads everything up into memory. And using pointers in the memory system allows us to, kind of quickly, without having to load it, quickly reference stuff. And the file itself, this file system is referenced through, actually I'm getting to this concept through an inode system, which is nothing more than a bunch of pointers to disk spaces that represents the concept of the file. So if we have a file descriptor and it's on a USB drive, we can create a pointer to it, and we can read and write to the drive without actually having to go to the drive. It's in memory. It makes it faster. So one of the things that Unix has done is, come up with this inode system. And the inodes themselves, kind of like the fat allocation table of a DOS system. So it's a fat allocation table. When you format your hard drive, you usually have to tell it what file system support you want on that hard drive. And do you want, what is it, net something or other, for network system support, distributed system support, FAT system support, extended journaling, all these kind of different options that you have. Well, the options are going to tell you how the stuff is stored on the disk. And traditionally, from a DOS perspective, from Microsoft DOS and Windows, the FAT was the traditional method. It's slowly changing from that. A network file system is actually still different. But what it was is like the beginning part of the disk was holding this table, and when you accessed the disk, it read the beginning part, found the information from a lookup table, a FAT allocation table, and then found the blocks that were associated with this file. So you actually had this like index that's written on the disk, and you constantly reading the index, going and finding the information, or reading the index, going and finding the information, or you're storing the index in memory, which is kind of interesting. So what Unix does is it takes the index off the disk, puts it into main memory, and makes the kernel responsible for it, which gives us, as I was talking about yesterday, the ability to mount different hardware devices, different file systems into the same structure. So we might have a directory tree that's basically referred to as the inodes. You know, what are inodes? Well, they're nodes in a tree, essentially, and the directory structure is a tree. And in the tree, we could have FAT32 files. We could have extended files, extended 2. We could have Mac files in there. And we could have all these different types of files that are all merged together in the same directory structure, all together. And if we separate out that abstraction and let the kernel take care of it, then we're looking at inodes, so, which is where that concept comes from. And inodes gives the kernel control over permissions and ownerships and modification dates. And then we're going into the stuff I ended with on yesterday, talking about, you know, the permissions and stuff like that associated with a file. So we have different types of files. In a Unix system, the file could be a regular old file, could be a directory, or could be a special file. We also have device driver files, or device files. If we have a symbolic link, as an example, the value of the symbolic link could be associated with a file. If it is a regular file or directory, it contains the location of the disk blocks that are associated with it. If it's a file pointer for a device, then it's the driver interface that's loaded for the device, so we can identify where it is in memory and what address to go look for from a hardware perspective. So, yeah, symbolic link is kind of an interesting concept because we don't actually have symbolic links in Windows traditionally. I don't know if Windows 7 supports this or not yet, but to have one physical location of something on a disk. In Windows, if you wanted to move it, you physically move the file from one entry in the directory structure to another entry. Or you copy the file, and you have two copies of the same file stored on the same hardware. That's kind of inefficient if you think about it, because you have wasting space with multiple duplicate copies of stuff. And then wasted energy in trying to move something, physically move block entries, or, you know, update the file allocation table to say, hey, now it's stored over here. Whether it actually moves the file, it's kind of interesting. I think it actually does move it, because you always see those little, you know, dialog boxes that come up and says, okay, copying this file, copying that file, copying this. Oh, what are you doing? You are moving it, you know, or is that just fake? Is that just, you know, telling you that the kernel is updating the file allocation table and it's taken a long time, so it's going to show you this graphic or something? All right, so in a Unix environment, we don't do that. We just update the inodes. When we update the inodes, we get a bunch of pointers to this stuff. We just change the pointers around faster, so we can actually, you know, accomplish a little bit of faster processing of that directory stuff. And then we can create what's called a symbolic link, which is an update in the inode table that has nothing to do with the storage. So now we have two different directories that this file is stored into, but it's really only in one place. But we have two entries in the file system structure in the inode table. Makes it easy. So inodes are pointers, and we have an indirect to the entire block, and their pointers are numbered by, the inodes are actually pointers to blocks. We have a double indirect pointer in a primary inode to a block that is just pointers to other blocks. So think of inodes as pointers. And we have pointers to blocks, pointers to pointers to blocks. So we have a whole structure of directories all filled out with pointers. So, and there's another lecture on file system structures. Well, probably not going to happen until the second weekend, and that will also go into the concept of the inodes as well. So the layout of the file system in a Unix operating system, the first block is normally referred to as the boot block. Same thing we get in Windows, the boot sector of the drive. Your antivirus programs are usually protecting that. So while the computer is running, it's going to block, lock the boot sector. What do you need the boot sector for anyway when the computer's running? So unless you want to load in, a nice little image or something in there, modify it around, which is, pretty much not allowed anymore because people discovered, oh, you can just put viruses there. So when you boot your computer, this scary little bug shows up on the computer screen for a few minutes. So that's the first logical block, and its purpose is to boot the operating system. And for a Linux environment, it's loading the kernel into memory. And then the kernel from memory is loading everything else. But you got to store the kernel somewhere. And actually, the kernel is not normally stored in the boot sector. It's stored off the boot sector, but the boot sector has got a pointer to go find it and go load it. So there's a lot of pointer information in the boot block section. The second block is the super block that contains the information about the free pages in the inode list. So we have the information to support the booting of the operating system, and then after that we've got the information for the file system support or the inode support, because we have to store that somewhere. And then following is the inode list, which is sort of like the fat allocation table. So the inode list, which is the list of inodes, the pointers to the pointers, essentially. So administrators, specific size of the inode list. When configuring the file system itself, you can set the size, make it big, make it small. It's kind of like list searching, if you think of the concept. If you have a huge list, it takes you longer to find stuff in it. The search space is bigger. So there's advantages to making the list small, which means you're going to have fewer number of directory entries. You have limitations. So if you've ever noticed why you can only go 32 subdirectories in, or actually I don't know what it is anymore. There is a limitation, however, in Linux and also in DOS as well, because the table can only store so many depths of information. And so you can only have so many subdirectories. You can have so many files that are in a directory. And then most people never come close to exceeding those limitations, so they don't know about them until they start writing files. Actually, there's a maximum file size, and it's controlled by the file system support, because we can't store enough references or pointers to something that's too big. So actually, in the old days, the disk itself was limited as well to 1 gig, and then we had extended, we had to update the technology of the file system to modify to accommodate for larger hard drives, essentially. So the kernel references the inodes by an indexed into the inode list, pointer list. The data blocks start at the end of the inode list, which is the data that we're storing the file systems with. And certain, they can contain file data and administrative data as well. So the conversion of the path name to the inode. So yesterday I talked about relative and absolute paths and stuff, and what you're really doing is traversing the inode list. You're working with the inode list, and you're trying to find where you are, and you're going relative to that location. You're navigating it. So we have a conversion process that happens because those inodes aren't storing, /b hecker. They're storing a NAMI, and the NAMI is associated with it's the algorithm that's going to parse the path name one component at a time and give us the real directory location and give us the pointer and information. So the algorithm is called NAMI, and it parses the file name, converts each component into an inode based on its name and the directory structure where it's being searched, and it eventually returns the inode of the input path name. So the initial access to the file is through its path name. The path name is converted using this algorithm. So the kernel mode needs to translate a path name to inodes to access the file, because it doesn't really store, home, users, bin. It doesn't store any of that stuff. It's got inodes, essentially. So the algorithm itself, if the path name is absolute, then it starts from the root inode. And if the path name is relative, then the search is started from the inode that's corresponding to the current working directory of the process, and keeping the process, under the area in which, or keeping track of what's going on in terms of that process. The components of the path name itself are then processed left to right. So we do read it left to right. It's just the way that we write it. Every component except the last one should either be a directory or a symbolic link, and then you can call the intermediate inodes the working inodes. So at any one moment of time, the kernel is keeping track of where you are in the inode list. And that pointer, the current pointer that you're on, is essentially going to tell you where you are relative to other locations as well. So if the working inode is a directory, the current path name component is looked for in the directory corresponding to the working inode. If it's not found, it returns an error. Otherwise, the value of the working inode number becomes the inode associated with the local or located path name component, and it returns the information you're looking for. It either gives you the file, allows you to manipulate the file, or basically changes your pointer in the where you are in the pointer list. So if the working directory corresponds to a symbolic link, then the path name up to and including the current path component is replaced by the contents of the symbolic link, and then the path name is reprocessed, I should say. So a symbolic link in nature is just a fake inode entry. I mean, it is actually stored differently because it's not a true link, and if you think of the concept, it's just a copy of a link. So when you make a symbolic link, you're copying a directory link without actually copying the directory. And it's still recognized as a symbolic link, so the inode algorithm is treating it as such and resolving it and then reprocessing once it figures out, well, what's the underlying real link location. So the inode corresponding to the final path name component in the inodes in there is referenced by the entire path name. So let's talk about mounting file systems. So I never found my USB drive, by the way, so I think I lost it. Those things are so easy to lose. But essentially what happens in most of your modern day systems is there's a command called mount, and there's a umount for unmount. And when you're mounting, essentially what you're doing is you're telling the kernel, hey, I have a new file system, I have a new drive for you, and we're going to put it into the file system. And the file system isn't on the disk, it's in the inodes. It's loaded up, and in the organization of the list, it's in kernel memory, and the kernel memory is being used to access the physical hard drive. So we're mounting file systems for use with physical devices. So when Unix is started, the directory hierarchy is corresponding to the file that's located on a single disk called the root device. So we always have a root device or root block, root sector, where it's acting as the single point or starting point for the file system entry. So the mount utility allows a super user or root user. Usually you have to have more than just a plain old user. I don't know. Modern day for USB devices and stuff, a user can mount the device no problem. But it slices the root directory to the file system into the existing directory hierarchy. You actually insert the disk instead of it showing up, well, I shouldn't say that because now in modern day Linux desktops it shows up as a separate device actually. It's, you'll say USB disk. We'll say, actually they put drive letters on them too, kind of like Windows. So we've ventured out into Windows look-alike desktops. But traditionally, the disk doesn't show up as a separate drive. It gets mounted into the file system. So file system is created on other devices that can be attached to the original directory hierarchy using the mount mechanism. So here's what the mount mechanism looks like. So when you mount, you are establishing a connection between the device and the file system, and you're loading the device into the file system. So when the mount is established, users are unaware of the crossing mount points, which means you don't know, going back to what I said yesterday, you don't know what disk it's on. It's just mounted into the file system. So you might have a directory, but you don't know what physical disk that directory is actually on. So the file system may be detached from the main hierarchy using the umount or unmount utility. So links do not work across mounts on system V. What are links? Well, if you have multiple mounts into the system and you're trying to make you're trying to make a link across it, so you can put 5 disks into one directory. Not supported on system V. Is supported on other operating systems, versions of Linux. Which means you can take a bunch of little small devices and make them look bigger, because you're mounting them all in there, and the directory spans all of these different devices. The files are actually physically stored on the different devices as well. So it's not all, the information itself is not stored in a central location. It's stored on all the different devices. This is actually what you're looking at the bottom of the screen is the syntax. So you're mounting a floppy at this mount point, and you're unmounting the mount point. So the kernel maintains a system-wide data structure called the mount table, and that allows multiple file systems to be accessed via a single directory hierarchy. We have the mount and the unmount command. Those are examples of system calls, actually. They modify the table. So the system call interface of the mount and the unmount is used a lot, actually. How many times are you putting something in, taking something out? There's a lot of programs that need to mount drives in. So with the mount, an entry is added, and the entry's got a device number containing the file system that the mounted disk is going to use, a pointer to the root inode of the newly mounted file system, a pointer to the inode of the mount point, and a pointer to the file system's specific mount data structure for the newly mounted system. So, common thing, a pointer, a pointer, a pointer. Which is why C programmers really need to learn about pointers and be familiar with the pointer concept, especially if you're going to write kernel code. It's all pointer. So everything's a pointer base. Because why load it into memory? You know, just for the same reason why we use pointers in programming in C. It's more efficient for some ways. You know. So what happens when an unmount or umount occurs? Several different checks are made in the kernel. We don't actually have to save anything to the disk unless we're going to unmount it. So as we're mounting a disk in there, and we're changing and we're manipulating, we're opening files and we're playing around with this stuff, eventually we're going to want to unmount it. And so to unmount it, it's going to check whether or not there's going to be any open files. You know, if there's any open files, it's not going to unmount it. It's going to say, hey, we've got open files. Can you close these files so we can save them and update the disk before we remove it? Because once we pull it out, we don't have that information available. We can't save it. So if there's no open files, then the system to do an unmount would be unmounted. Flush the super blocks and the buffered inodes back into the file system. So close back up all the inodes you opened up, get rid of those pointers. The pointers don't need to be in memory because the files aren't there anymore. The disk is unmounted. Remove the mount table entry and removes the mount point that is marked from the mount point directory. So going back to the concept of the file descriptor for open files, well, we've got a mount point directory, that mount point mark, that is really a file or a mount description, or, you know, it's a description of the location in memory, temporary memory, where this mount is actually occurring, which we're reading and writing to the memory, actually. So makes it faster, actually, because we're not reading and writing to the physical disk. We're using an abstraction of it. We have to sync it, we have to store it, which takes up time. So you'll notice on a Linux and Unix system, when you put something in, like for example, you're just playing around with a USB drive, you put it in, it takes longer for it to register. You pull it out, it takes longer for it to register. But while it's running fast. So, which is actually sort of similar to what Windows is doing now too. So you have to eject. Well, it takes longer to eject it. You put it in. Where is it? It takes longer to be in, because you have to like set up all of the overhead from the kernel perspective to make that thing work. So, which is why people don't. Well, some people don't like to load operating systems from USB drives. So, can't do very much with it, but they're getting better and better and bigger and bigger and faster and faster. So, another thing that the kernel does is keep track of running processes in the system. So here's the process subsystem with process states, and people who take systems programming. And you go, well, what's systems programming versus programming? Well, systems programming is Unix programming. What's Unix programming? Process programming, mostly. System utilities. There's system utilities doing, well, they're taking advantages of multiple processings, multiple threads that can be used for processing. If you go back to the concept of CPU scheduling, in order to understand the way the process subsystem works in Unix, it's all CPU related. And going back to what I said about CPUs, at any one moment in time, only one instruction is running on one CPU. We don't have multiple instructions running simultaneously. So instead, we take all of the requests for CPU and we separate them out into threads of execution that are associated with processes, and then we have kernel mapping. So one process might be mapped to several kernel threads for processing, then if that's the case, we might have several different threads that are scheduled to run to service a process. And that's how we get higher priority processes, more threads associated with it, or more CPU time in the scheduler. And we can put process numbers for priority on those threads and on those processes. Long story short, we're looking at sharing the CPU power. And in order to do that, we have to juggle the process states. Because at any one moment of time, not all the processes are going to be running. So for every process on the system, there can be up to 6 states. And these are generic. You could probably break this down out into certain ones that exist more than others and stuff. But it's going to be running if it's currently receiving CPU time. If it's currently using the CPU, it's running. It's runnable if it wants to use CPU time, but it just isn't given it yet. So if it's ready, so depending upon priority, it might be sitting there ready to run, and then we have latency because we can't run it because the processor is too slow. It hasn't finished the last job it's working on or something. We could have threads that are sleeping, waiting for an event to occur. We could have suspended threads, such as resulting from a Control Z that was hit on the keyboard to process a command that says suspend. We could also have idle threads, and they are being created by fork but not runnable, which means we haven't assigned them any work yet, but they're ready. Well, they're not really ready, they're just idle. They're sitting there. The line of code to actually run them hasn't been hit yet. And then we have zombied processes. They're terminated, but the parent has not accepted its return value, which means the parent's never going to, well, it's zombied. It can't go away. It can't be taken out of memory because parent can't clean it up. So we also have different types of processes that run. As an example, the foreground process, the background process, the daemon processes, and stuff like that. And we talk about processes with Unix because it is a multi-processed, multi-threaded environment, more so than Windows. We can't program with processes on a Windows system, but we can do it on Unix. So here's an example of the process states. For example, when a process issues an I/O command, it becomes suspended, then it becomes runnable again when the I/O completes. And it depends on the priority of the process as to when it's going to get the I/O, when it's going to be serviced. So the process composition. So as I was saying before, going back to the kernel concept, we have a program. It's a C program, our assembly language /C. It's written. And we take the program, we load it up into memory, and we call it the kernel. Okay. And the kernel is there, and it's got pointers to other things, and it's just a program running in memory. Well, all of our user mode processes are programs that are running in memory. It's just the memory abstraction. So when we double click on something to start a new process, run a program, first thing it happens is it opens up process space, and the process space is divided out into these different areas. And the process space is memory allocated to code, which is the executable text portion of the process. So it's the instructions that are going to be running. The data area, that's used to process certain static data. The stack area, that is used by the process to store temporary data as well. And what are we doing? Storing data, storing data, storing data. It's kind of like pointer, pointer, pointer for the inodes. So we have the user area, where it's going to hold the housekeeping information. Page tables used for memory management. So we have this organizational scheme for the process, and the kernel keeps track of this organization and actually creates the scheme for us and loads the information in to the processes. So the user area. So every process has private user area for housekeeping. So the information is used by the kernel process for memory management for all sorts of different things, or process management I should say. And it's really just code specific towards what the process is doing. It contains the control and the status information of what's going on in the program, because we have to actually have some way of loading that up into memory. Because we have multiple processes that are going on, and not all of them are running simultaneously. So we have to switch back and forth between the different processes. So we need data storage area in that process space to keep track of this information. It contains the user area. The contents of the user area are only accessible when the process is actually executing in the kernel space. So when it's not executing, we can't really get to that. And And the kernel can only access the user area of the current running process and not the user area of other processes. So it's constantly pointing to different memory locations for different processes that are supposed to be running and updating each one of them individually. If we keep them all separated, that's how we can have multiple programs running simultaneously. So we can have Microsoft Word up there, and the information for Word isn't going to interfere with PowerPoint, isn't going to interfere with the text editor, or something like that, because it's all stored separately in terms of its process space. The important fields in the user area include, well, what are they? A pointer, here we go, pointer again to the process table, where the current executing process is stored, because a process table, a PC process control block, and process tables that the kernel is managing is keeping track of the memory locations of all of the processes. And in the processes themselves know how much time that they have left and how much time or what they're executing and what current instruction has been executed last and stuff like that. The process might have open files, and if so, the user area is going to keep track of the file descriptors for all of the open files that the process owns. Any I/O as well, internal I/O parameters, current directory and current root, process and file limits, perhaps real and effective user IDs could also be stored in here. Array of indicating how a process reacts to signals and how much CPU time the process has recently used. How much CPU, what does it have left? So I've been mentioning this process table, which is a kernel structure that keeps track of all of the processes in the system. So it contains an entry for every one of the processes. At any one moment of time, the process table is going to look different because we don't know what's running. So it's like in a Windows system, when you go Control-Alt-Delete, you can go into the task manager and you can see what's running. Well, that's really a process table, if you think of it. We don't have that feature really in a Unix or Linux environment, but we can type PS, as I showed you yesterday, and see all of the processes running, or jobs for users. So the process table contains files that must always be accessible to the kernel. Actually, PS is a command. Is a system call interface, actually. It's a system command. You type P as in Paul, S as in Sam, PS, and you get process states. And so it's going to the kernel, asking the kernel, hey, what's in your process table? And it comes back and says, here's what's in my process table. So it's kind of interesting. So process entry information, we have the state of the process, the running, runnable, sleeping, suspended, zombied, idled, all that stuff. Process ID, the parent process ID, the real and effective user ID, the group ID, all of the information I talked about yesterday in terms of the changing the owner and changing the user. The location of its code, the memory where we got the stack and the data and everything else that's being used. A list of the pending signals that the process is supposed to be dealing with. Various different timers that gives process execution time, kernel resource utilization, all sorts of different things. So processes are useless unless we can run them, and the way that we run them is through the CPU scheduler. So the kernel also has the scheduler as a concept. So the scheduler is responsible for sharing the CPU time between all of the competing processes. That's why I say if you have multiple different CPUs and you have multiple schedulers attached to the CPUs, then you have multiple processing going on. If you only have one CPU, you only have one process running at any one moment of time. So the scheduler maintains a multi-level priority queue that allows you to schedule processes efficiently and follows a specific algorithm for selecting each one of the processes that should be running. So here's where we get differences between different kernels. We can configure a kernel, and we'll talk about the concept of the process control block. Well, that's really a data structure. Talked about the concept of the CPU. Well, that's really an algorithm. So the CPU scheduler is an algorithm that's running. So we can tell the kernel, use this algorithm instead of that one. And one algorithm might be using, in the case of Unix, most kernels are using a multi-level priority queue. And then multi-level because they have short-term, long-term, medium-term schedules where processes, that first enter into the system go to one of these queues and it waits. And then ones that are I/O bound might go for I/O, and ones that are CPU bound might go wait in the CPU queue. And we can put different priorities on these processes as well. All the kernel level instructions, well, they're going to get run first, and all the user stuff, well, they'll get run second. And the algorithms that are selected for this can be customized. In fact, you can write your own CPU scheduler. So grassroots people who like to build kernels like to play around with stuff like this. Like to modify the algorithm code that does your CPU scheduling to change the routine somehow. If you do that, then you can actually make application level support for this. So let's go back to the concept of the temperature controller, and we're building a kernel that's going to go on a little box that's going to control the temperature in the room. Well, we can change the CPU scheduler of that to, make sure that the heater, all those processes that are associated with turning on the heater, or have a higher level priority to them, or in the user mode. So if the user stood there and started pressing buttons, it's all going to be ignored, or it's all going to be that process that processes the user input is going to have a lower priority, maybe, or we're going to kill that process while something else is going on, and it'll say waiting, quit pressing stuff, we're waiting. So it'll just ignore it actually. And those are scheduler rules, and the scheduler is processing the requests from the user. It's performing the functionality that the processes are doing. And in the case of the heater control, it's turning the heat on, turning the heat off. I don't know what else a heater controller does really, but maybe picking up sensor information perhaps as well. So the kernel allocates CPU time to the processes, and the time is really called a time quantum. How many ticks? How much time does the clock how much clock time is going to be allocated for the CPU for this particular process? It preempts a process that exceeds its time quantum and feeds it back into one of the several different priority queues that might exist. So during every second, a process in a non-emptied queue of a high priority queue or allocated CPU time in some sort of a round-robin fashion. If you take an operating systems course, you'll see all about CPU scheduling and schedulers in general. Round robin is just kind of a fair kind of way of doing it, just hopping to each one of the queues and running the next process. It's kind of a way of batch processing all of the information. The goal to the entire scenario is to load a process into memory, put it in the process control block, schedule it, and get it out, and then take it out of the process control block. So it's really an assembly line, essentially, of execution that's going on the computer. So to support real-time processor, schedulers need to be changed, and they need to be changed so that the scheduling is based on priority inheritance rather than on time quantum. So going back to that temperature controller, if something else has to happen, it's going to be based on a priority, not, well, the heater hasn't had enough time, otherwise it affects the user interface and affects the processing of the system. So it's kind of it's an interesting circus, or interesting orchestration of different events that are occurring, and schedulers make the system seem slow, or they make the system seem fast. They provide the user experience, long story short, because what are we doing? We're, when we double click on an icon to open up Word, we want it to open. So if it opens quickly, oh wow, nice user experience. Opens slowly, well, not so nice. So also more preemptive points for the kernel are needed for real-time processing. Real-time processing is taking events that are coming in and processing them immediately. Real-time processors, you can build a Linux kernel with a scheduler to do real-time processing, and then you've got like a port sniffer, or you've got a tool or a utility that happens that is like a video camera or surveillance system that's monitoring, and it's giving you feedback that's happening right now. It's capturing video, or it's sending out service calls or something. Okay, so as I mentioned before, the kernel's got to keep track of all these processes. And it sends all the processors to the scheduler, and the scheduler gives them CPU time. The CPU time makes the processes run, and then the processes finish their execution, hopefully, and they get out of the system. They get removed from the process control block, and then they go back. They're out of memory, and we're ready to run another program. So the time it takes to switch between the different processes is referred to as context switching. So the context of one process running and the memory that's being used that's associated with the one that process is running, that the scheduler is aware of and the scheduler is handling, well, that process that's running right there is in a different context. So we switch the context from one process to another. The kernel has to save the program, the process's program counter where it was in the instructions that it was running, maybe a stack point or maybe other information about the processor's user data and stuff, temporary information, whatever's going on. And then when the process is ready to run again, the kernel has to go get that information and load it back up. That's time consuming. The more context switching that occurs, the worse the user experience. So as a scheduler goal, we want to reduce context switching because it's wasted idle time. It's the light on the box when nothing's happening. What's going on? Well, we're saving one process and it's loading another process, and it's saving another process and it's loading another process. So it's kind of like swapping. Swapping in terms of memory management slows the computer down. You might think, well, that's odd. Why do we want to swap? And actually, it just has a side comment because it's not mentioned in the slides that I just realized. Swapping is kind of a Unix thing, Unix Linux thing. So in the old days, and still today actually, we don't have that much memory. Memory is like a conservative resource. Well, nowadays, I mean, we got 4 gigs of memory. I was like, that's a lot of memory. That's good. But we have bigger programs with bigger memory requirements. So as memory gets bigger, well, so do the programs do. So actually, for a Windows 7 system, if you don't have like at least 4 gigs, you're not, your system's not going to be running that nicely. Maybe I don't know what the specs are. I think it's like 2 gigs minimum now. Well, in the old days, we didn't have anything. We had like 256K, 512K. We didn't have that much memory that was going on. And so the concept of the swap drive, we took a piece of a hard drive and we created a memory abstraction on that hard drive, and we called it a swap disk. And the swap disk, it acted like pretend memory. And the pretend memory was formatted the same way as the main memory. And we were able to load stuff into the swap area as if it were loaded into main memory. But going back to what I was saying earlier in terms of the memory, the farther we get away from the CPU, the slower the memory runs. So if we're using a swap disk to mimic RAM that we don't have, and we're loading and unloading and loading and unloading and constantly updating the swap, it's kind of equivalent to context switching in terms of what the processor, what the CPU is doing with all those processes when it runs a process, stops a process, runs another process, stops a process. So context switching and swapping are 2 examples of how the kernel can be configured to optimize or to run slowly, actually, depending upon what needs to be done. So you turn off swapping, you're limited on your RAM. You can't turn off context switching, you're limited on your processing. So your pros and cons. You can't turn it off, you have to use it. So the algorithms that are associated to it can be configured, and people build their own algorithms and they custom build their own kernels to, take advantages of different things. So in terms of loading an executable, going back to that user mode, so I've talked a lot about the kernel mode so far and what that's responsible for. Oh, the only thing that happens in the user mode is we start programs. We double click on stuff and it runs, right? So we have to load an executable. And an executable is anything that's runnable. So the user compiles the source code of the program, creates an executable file, which consists of several different parts. We have sets of headers that describe the attributes of the files. We have the program text and machine language interpretation, representation, and then we have other sections such as symbolic table information. All of the information that's being used by the kernel to support the kernel runtime. And the runtime is referring to what happens after you double click on the file or you type the command of the file, and the kernel takes over. And the kernel makes the process abstraction, makes an entry in the process control block, sets the memory information, and then schedules the process to run on the CPU. And so the scheduler is working now, and then it's performing context switching to go in between the different processes. The generic term for all that is runtime environment, and the runtime environment is controlled and orchestrated by the kernel. So the kernel loads the executable file into the memory during the exec system call. So the system call interface is actually being invoked. Whether you fork a new process or not, one is created for you automatically. The exec says run it, execute it, which means load the process, which contains the 3 different parts or the 3 different regions in memory. And that's where we get the typical runtime environment. And this is actually kind of a similar model that's used in a Windows system as well, where we have the text, the data, and the stack. These three parts of the runtime environment correspond to the different sections of the code and the different sections of the memory that's associated with the process. So text corresponds to the text sections, data for the data sections, and the stack is automatically created, and its size is dynamic, just as the kernel is processing the information at runtime. So at any one moment of time, the kernel might be processing 5 instructions or 4 instructions or something, and those would be loaded on a stack structure, and then the stack would be executed so that the information could be given. So loading an executable, the compiler generates an address with a virtual address space with a given address range. And then we have the memory management unit that translates the virtual addresses that are generated by the compiler into the addresses of the physical memory. So this is kind of the interesting way that the kernel juggles processes, CPU scheduling, and memory management all into one. So going back to the concept of swapping, as I mentioned before, it's really a memory management concept. And the memory management is really an artificial concept that was created by the kernel anyway, because at any one moment in time we're not actually using the physical address space that's associated with the memory. We're using a virtual abstraction of that. Because going back to the concept of memory and how that's being used, it's all an abstraction, and it's an abstraction of holding data, processing data. So if you think of the concept, computers are really elaborate calculators. We're putting data in there and we're processing the data. And the memory is essentially facilitating that. So in terms of loading the executable, it gets loaded into virtual address space, and the virtual address space is mapped through the memory management unit. And the memory management unit is keeping track of the physical physical memory locations. And if the kernel is made to read from the memory management system as a kind of the MMU is kind of a generic concept, then it always looks the same. So if you think about the concept of memory, it comes from different manufacturers. We load it into banks. It has a different abstraction depending upon the architecture of the board that we're reading and writing, we're looking at. And we'd have to create a kernel for every vendor out there. We'd have to create a kernel for every configuration that was possible. Instead, we read from a memory management unit. It provides a more consistent abstraction, and then it does the translation for us into the physical addresses. So it makes it more generic in terms of the memory usage. So going back to the concept of building your own kernel again, well, we can optimize the memory management to turn on and turn off certain features so it's not generic. So we can make it more specific towards the usage of the physical resources that we have. If we do that, then we can make a faster system. Because what do people want? They want programs to run fast. They want, the kernel to load fast. So in order to start the entire process, we have the boot and the init process. So as I'm bringing this full circle all the way back around to the beginning of this lecture, when I started talking about the boot sequence and the kernel as being the first thing that loads, it really is actually. So the administrator initializes the system through what's called a bootstrap sequence. Bootstrap is sort of like a sequence of events that's going to occur, and it's usually stored in a savable kind of thing, so it runs every time you reboot the computer. The bootstrap sequence reads blocks of the disk, loads them into memory, processes the information, creates the kernel mode, the kernel mode creates the user mode, and voila, we double click on files and we have stuff running. So the program contains a boot block that loads the kernel from the file system, for example from Unix. After the kernel is loaded into memory, the boot program transfers control to the starting address of the kernel, and then the kernel starts running. So we got a small section of the disk. The boot sequence looks at the section of the disk, finds the file location, it's usually a pointer, to the system block where the kernel is actually stored. Starts the kernel, which I mentioned before is just a C program, C and assembly language essentially, runs the program. So our entire operating system is a starting of a program. And the program loads stuff into memory, and the entire process runs until we turn it off, essentially. So, in terms of the boot process, after the initialization, the kernel mounts the root file system and handcrafts the environment for process 0. So the process numbering starts with process 0 forks within the kernel itself. And then we have process 1, where the user running in kernel mode creates the user level context. So process 0, or the beginning, is the kernel mode. Process 1 is the start of init, or the initialization of what would be considered the user mode. And so after we have the user mode, we allocate the data region by attaching it to its address space, and we create the abstraction of the user mode from process 1. Which is kind of interesting because by the time you make processes, you're at the 3000 level or the 4000 level. And if you remember yesterday I was running the process, the PS command, when we were looking at the process IDs, they're pretty high up there. But yeah, you got to think, that doesn't start at 2 or 3 or 4 or 5. After you get to a certain point, it's just going to arbitrarily pick a starting address to use for the numbering system. So process 1 copies the code from the kernel space to the new region, where it forms the new user context, or process 1. It also sets up and saves the register context, and then it returns from the kernel mode and executes the code just copied from the kernel to create the user mode. And then process 1 is now the user level process. And the text code consists of a call to exec, which is the init program. So init is the initialization that creates the shell, or the script that's going to run to essentially create what we're calling the user mode. So, as promised, it is a quarter to noon, and we're going to take a. I think this is where we stopped yesterday too. So, this is the end of lecture number 2, which was on the kernel mode and kernel mode processing. I don't believe that last slide had anything of significant value on it. I'll just go back to it real quick. And nope, more on the boot sequence, more on customizing the kernel. So at this point, 11:46, we should take, I don't know, we think about an hour, or take an earlier lunch today. Because it's quarter to noon. So we can come back at maybe 45 minutes, 12:30? 12:30 work? Or do you guys want longer? Well, that's actually, it's 45 minutes, not an hour. Oh, okay, we'll call it, how about 12:45? Okay, somewhere around 12:45 we'll start back up again. And what do I have for you next? Well, we're going to take the init process a little further. I'm going to talk a little bit more about what happens after the boot sequence, which is really our scripting. So yesterday we talked about the concept of scripting, looked at different scripting languages in terms of what they're used for, in terms of the environment. After the kernel loads and creates the user mode, we have a bunch of scripts that run, and those scripts are setting the environment and really creating the user experience for us. So after lunch we will take a look at scripting in terms of the init process and the customization that occurs, and then get into some miscellaneous Unix concepts as well. So that's the end of lecture 2A, and it's the beginning of our lunch break. I'll see you in a few.